In this video, we will look at trig identities and also at using trig like algebra in statements to simplify and solve things. I've written up a definition of identity. An identity in mathematics is not how you feel about yourself, but it's a mathematical statement that is always true. So, for example, the distributive law is a good example of a type of identity. Right? If I have 2 times x plus 3, that is always true. It is always true that that's equal to 2x plus 6. So you could think of that as a type of identity. Okay? In trig, we also have certain things that are always true, and some of them you've already come across. First of all, we have this one that we also learned from the sine law, that the sine of an angle is going to be the same as sine of 180 minus that angle, because in quadrant 1 and quadrant 2, sine is always positive. So that's one we've looked at before. We also know that the tangent of an angle is the same as the sine of an angle over the cosine of an angle. A new identity in this section that's always true comes from Pythagoras' theorem and uses the unit circle. We take a triangle on the unit circle and remember that the x-coordinate to this point is always x, and the y-coordinate to this point is always y, and the radius of this circle is 1, then we can see that x squared plus y squared should always be equal to 1 squared. And we also know that cosine and sine can replace the coordinates, so that means the cosine of the angle squared plus the sine of the angle squared should also always be equal to 1 squared, or just simply 1. And so that's our new identity. And usually we write it with sine first, rather than with the x squared. But sine squared plus cosine squared of theta always is equal to 1. And that identity can be rearranged in lots of different ways in order to come up with other identities. So I could, for example, subtract sine squared from both sides and get cosine squared theta equals 1 minus sine squared theta. You can do that in a lot of different ways, and your textbook lists them all if you want to go and look at that. So that's the one part of this chapter. And the other part of this chapter is that we can treat trig expressions like little bits of algebra. For example, if I have 5 sine theta plus 2 sine theta, and I can treat the sine theta a little bit like an x, like 5x plus 2x. And so the answer, or a simplification, it's not an answer yet, but I can simplify that statement by adding the number of sine thetas I have together and getting 7 sine theta. Just like we would add the 2 like terms here and get 7x. That also goes as far as expanding things as well. If I had a statement like sine theta plus cosine theta, and I squared that whole statement, then I can square it just like I square algebra, by taking sine theta plus cosine theta times sine theta plus cosine theta, and then getting the resulting expression, expanded expression. First term, sine times sine, is going to be sine squared theta. Outside terms will be sine theta times cosine theta. I just write it together like that. Inside terms will also be sine and cosine multiplied together. It's in the other order, so I'll just flip them around for now so I have like terms I can add together at the end. Remember, multiplication is commutative, so you can switch them around. And the last term is cosine theta times cosine theta, so that's cosine squared theta. Okay, and I'm almost done, but there are some things I can simplify. First of all, in the middle here, I have 2 like terms. And then on the outside, sine squared theta plus cosine squared theta, I'm going to use one of my identities, the last one that we looked at, to turn that into 1. Remember, sine squared theta plus cosine squared theta is 1. So let's take that as 1 plus, and here I've got 2 of these terms in the middle, so sine theta, cosine theta. So you can see combining identities with a bit of algebra properties and treating them like bits of algebra. Here are some more examples. Let's do an example. This is from your textbook, so you can also follow along in the book. 3 minus 3 cosine squared theta. Here I can factor, just like I can factor algebraic expressions. So I'm going to take a 3 on the outside, and then 3 divided by 3 is 1. And the second term divided by 3 is going to be cosine squared theta. The advantage of doing that is 1 minus cosine squared theta is one of our identities. If I subtract cosine squared from both sides, going back to here, even farther back, to this part here, if I subtract cosine squared from either side, I get 1 minus cosine squared on the right-hand side. And that's equal to sine squared theta. So here I can replace this, I didn't mean to erase it, I meant to replace it. I can replace this with sine squared theta. And that's going to be equal to 3 sine squared theta. And that's a little bit simpler than what we had to begin with, so we'll accept that as a simplification. I can also factor out bits of trig. If I have cosine cubed theta plus cosine theta sine squared theta, then the common term here is not a number like 3, it's actually a cosine theta. So I can take out the cosine theta, and then I get cosine squared theta plus sine squared theta. And there I have my identity again, because that's equal to 1. So that's 1, and 1 times cosine theta is simply just cosine theta. Okay. A few more examples that require more complicated factoring. Let's do this one. This is actually a quadratic with a sine function. So I have a squared term over in this term, a single term over here, and no sine theta here. It might be easier at the beginning to treat this like algebra and actually make a substitution and say, let's call sine theta, let's simply call that x. Because then I can call this x squared minus 5x plus 4, and it looks a little bit more familiar. This is factoring. I'm going to look for what multiplies to 4 and adds to negative 5. Since there's no term out here, I don't have to use any splitting up the middle term or anything like that. So I'll look for what multiplies to 4 and adds to negative 5. That's going to be x. You know, I've thought of it already. X minus 1, x minus 4. And then once I have it factored, I can put my substitution back in, because of course this wasn't x to begin with, this was sine theta. So I end up with sine theta minus 1 times sine theta minus 4. This is going to become important later on when we start solving quadratic equations. One last example, and then we're done for examples here. I can also do this if I'm dividing parts of expressions out. So let's take cosine squared theta minus sine squared theta. That looks like I might be able to find an identity, but actually if you subtract them, you can't. They stay exactly as is. And cosine theta minus sine theta. So I can't just use an identity for that top, but I might be able to factor it. What I have here is a difference of squares. If you take cosine as a variable, let's call that x, and square it, and subtract another variable, let's say y, and square it, you'll see that's a difference of squares. So cosine squared theta minus sine squared theta, we can factor as a difference of squares, and that will make it cosine theta plus sine theta, and then times cosine theta minus sine theta. That's all over cosine theta minus sine theta, and since that's one set of things, two terms subtract from each other, and over here I have that exact same term, I can actually cancel them because those will be the same two numbers, and I'm left with a slightly simpler statement here, or at least it has no denominator anymore, of cosine theta plus sine theta. So that will give you the exact same answer as this first expression up here. Okay, that's it. We're done for examples. You're ready to get started on section 10I.